Okay, we're back. We're going to work on 1.3 linear functions, slope and applications. I'm not sure if this is going to run into two parts or not, so we'll call this part 1 for sure. And if we go into a second part, we'll label it separately as well. All right, so just a quick reminder, we have had the standard form that we know about, right? Our ax plus by equals c, where we have the a, b, and c are all constants, and they all cannot be equal to 0. Now, if I were to say 0x plus 0y equals 0, while it's a true statement, it really doesn't tell us much other than 0 equals 0, which is not particularly interesting or helpful. All right, so linear functions, slope, and applications. When we talk about linear functions, I want to be really super clear. We are talking about a straight line. It has no curves, no bends, no abrupt changes in directions, no wiggles, which is one of the reasons why I say I can't draw a straight line to save my life. It can be written as a slope in our slope-intercept form, which is a new form that we're going to be talking about. I've kind of introduced it before, but we're going to get real formal about it now. It's a different form of the line. We're talking about the equation of the line to our standard form. So our m is a constant that stands for slope, and then our b is our y-intercept. All right, those are two different things that are going to be like pieces that you're going to need to be able to plug things in to be able to solve things. Now, this is a little bit of a mini cheat sheet here. So if our slope is 1 and our y-intercept goes through the origin, so our b is 0, what we wind up having is our f of x, or our y, right? Our y is going to equal x, because 1 times x is x. So no matter what my x is, that's going to be my y. All right, but that has to be if these two circumstances must be met. M has to be a 1, slope is a 1, and your intercept is a 0, your y-intercept. All right, so if m is 0, all right, the function is a constant function. And we'll talk about what that looks like in just a second. But here, you'd have your y of x or your f of x equal to the y-intercept. If you think about that for just a second, it becomes pretty clear that that's a horizontal line, right? This is a horizontal line, and can be written like y equals b or f of x equals b, where the b is an actual number. Now, horizontal lines are always functions. Remember, we talked about relations and functions. Horizontal lines are always functions. In fact, every line except one is a function. All right. So vertical lines, they're given by the equation a or x equals a, right? We're not looking at y anymore. We're looking at x. They are not functions because they're passing through one input, and you get infinitely many solutions to that for an output. So that is clearly not, one input, one output sort of thing. All right, so vertical lines are the only case that lines are not a function. All right, so we've talked briefly about our linear function, right? We talked about y equals mx plus b, or f of x equals mx plus b. Slope, here is what people can get confused when they hear all these different terms. These all mean exactly the same thing, okay? And so I'm just going to run through a few of them. I'm sure there's some that I've omitted, but I want to make sure that we get the really popular ones, or ones that people are likely to see. So m is slope. Our delta y over delta x. If you're in sciences at all, if you're talking about medical stuff at all, the delta means the change in. So you're going to have the change in y over the change in x. That's what that delta x, or the delta y over delta x means. Here we have y2 minus y1 is going to be divided by the quantity of x2 minus x1. The big thing to keep in mind here is my pair has to stay together, right? This pair, my x and my y, have to be the same x and y as it's originally given, right? We don't get to mix and match. However, it does not matter which way we go about this. You can have y2 minus y1 over x2 minus x1, or you can have y1 minus y2 over the quantity of x1 minus x2. Okay, so the point itself, which one you start with, does not matter. All right, but it is important that you keep the pair together. That's the big thing to take away from that formula. We also refer to it as the average rate of change. Sometimes it just gets abbreviated to rate of change, or rate. Slope, the word slope. Rise over run is another one that you may encounter. So that is, in a nutshell, many of the ways that you can, I won't say all the ways, but many of the ways that you can refer to slope. All right, so here I'm also talking about what's actually happening. Remember, I'm looking for this line, right? And in order to know how that's behaving, I need to know how far you go over and how far you're going to go up. All right, so rise over run, and here you have you're going from here to here on your Pythagorean theorem, right? This would be your A. Here's your B, right? And so that's going to give you your C. This tells you how fast things are going up, or if it were going this way, it would be how fast it's going down, how fast it's decreasing. All right. Talking about our slope, here's a real life example. We're going to have a linear function. As you see, we can do it with equations, right? We can talk about equations. We can talk about lines in terms of data, or data points, right, in a table. We can also talk about it in terms of a graph. Now, there's one thing I want to point out. Here's something called NB, or nota bene. It means pay attention to this, right? This is an important note. And that's just for future reference in case you're ever reading something and it says NB. Now you know what it means. In real life, data is not perfect. So you're going to have things that are really, really close, but you may have things that are not exactly perfect. They still may be operating as a linear function. So if you have, something that's just like a tiny bit off here and a tiny bit under here, this one's perfect, and then you have one that's just a little bit off here, that doesn't mean it's not a linear function. People make mistakes when they're writing stuff down, or when they're taking, timing something on a stopwatch or whatever. So yeah, in real life, data is not going to be 100% perfect. So just be aware of that fact. Now, if you wanted to get into how far off is okay, that would be a course in statistics. So in case you're interested in that, that is how far off you can be, and still think you're okay with the values. So here I'm going to have to figure out my slope, okay? And I'm going to pick 2 points, and then I'm going to pick a point from my graph, okay? So I'm going to go up, and I'm going to turn this red so that you can kind of see that my red values here. All right, I'm going to make my life easy. I'm going to go with the 350 minus 50, right? Those are my y values. And now because I picked my 350, I have to go with 70 minus 10. So I have 300 divided by 60, which when I reduce, right, I'm going to reduce that down to a 5. Now let's say I'm like, okay, well, I'm not sure if I believe that. So I'm going to take a smaller distance. I'm going to go from my 50 to 15. And I go on my graph and I plot it out, and okay, yeah, there's my 15. We're going to call that 75. So I have 75 minus 50 over 15 minus 10. That's going to give me 25 over 5. And sure enough, our slope is 5. Okay, and I probably should have changed my color on that, but oh well. So just circle this one in black. Or ellipse this thing in black. Right? So that's what a linear function looks like. There's a lot of ways you can express it. Here we're looking at a nonlinear function. And if you take a look, even though I'm going up by tens here, I'm going up by different numbers each time. So here's my 20, here's my 40, here's 60, 80, 100, and so on. Now, I do want to caution people, if you take a look at some very close numbers, right, you might make the mistake of thinking that that is linear. Like this little tiny bit is really kind of flat, right? And so if you're only looking at these couple of points, you might make the mistake of thinking that it's linear, where if you keep going, you're going to have more points. You would wind up seeing that it is not, in fact, linear. All right? So nonlinear, again, they're going to have curves, they're going to have wiggles, they're going to have sharp angle changes. You know, it's not going to be a straight line. All right, so I'm actually going to pause this. I'm going to go on to part 2 here. I want to make certain that I'm not overwhelming people with giant videos.